So when we're looking at mathematical models, we want to be able to look at the derivations, not necessarily because we need to be able to rederive the equation. The important part is the equation, of course. But the important part of the derivation is it tells us what assumptions are made about this when we construct this equation. So let's go back to ligand binding. And so remember the hyperbolic ligand binding equation. So we're going to go over this real quick, where theta is equal to the concentration of protein ligand complex, excuse me, over the initial protein concentration, or the total protein concentration. And that's equal to this, where we can fit our data to figure out where we can vary the, and experimentally what we would do is we would vary the ligand concentration, which is the initial ligand concentration, and then we would find some way to probe the experiment or experimentally determine theta, and then that allows us to fit the data in order to find this parameter Kd, which is important for letting us know, giving us a quantitative measure of how well a ligand can bind to a particular protein. So how do we get there? So first, let's start, we're going to erase all this. Let's start over from the beginning. Maybe we can get all this mess off. Okay, there we go. Okay, let's start from the balanced equation. Okay, it looks like this. P plus L, we have an equilibrium to form the protein ligand complex. Okay, we know that Ka, we know what Ka is equal to, but we're going to actually set this up as Kd, so the dissociation constant, which is, let's start from here, Kd, big Kd, of course, is equal to, at equilibrium, the concentration of free protein times, at equilibrium, times the concentration of free ligand at equilibrium over the amount of protein ligand complex at equilibrium. Okay? So this is different. So if we think of our concentrations as initial and at equilibrium, we can always think about the concentrations from an initial state and the equilibrium state. So we start with protein. So if the initial protein concentration is equal to P naught, as shown here, at equilibrium, that's going to be equal to the amount of protein that remains free and is not bound. So we denote that as the concentration of P equilibrium plus the amount of protein that is in the protein ligand complex at equilibrium. So that accounts for the total amount of protein that was there when the reaction started, so when equilibrium started. So we also want to do the same thing for ligand. So ligand naught equals, again, the amount of free ligand at equilibrium plus the amount of ligand that is bound to the protein. And that accounts for all of our ligand. Okay, that was there at the beginning of the reaction. So now what do we do with this? So experimentally, what we do is we have a set amount of protein. So for instance, let's say for our experiment, we say we have ligand at concentrations of 5, 10, 15, and 20 millimolar were added to 5 micromolar protein. Okay, so we have here, we have different ligand concentrations. So these are all not, and we have initial protein concentrations here. All right, so what we're going to do is we're going to vary the initial ligand concentration versus the initial protein concentration. So these are constants, these two values here. What changes, and what we cannot know until we do the experiment, is what's the final concentration at equilibrium of either the protein, the free protein versus the amount of protein that's in a protein ligand complex, and the amount of free ligand that remains after equilibrium is established, and again, the amount of ligand that is in the protein ligand complex. So these are things that we need to determine experimentally, okay? And so we get a plot, and we want to fit data to some sort of mathematical model. So we need to form this mathematical model, and we will do that now in the next video.